this is a 48 volt battery inverter or 72 cell PV direct inverter, meaning that this inverter will actually run without a battery but straight from a solar module that can give you at least 30 volts to around 50-60 volts. Right, this area here is the input area, and solar module supply, the circuit breaker, and then it goes to the power switch modulation IC, which drives MOSFETs, pumps the supply to 300 volts thereabout, from 200 to 350 volts depending on your settings, using this transformer as a push-pull power supply or push-pull DC to DC converter. Right, and then here is the full bridge MOSFET arrangement here, and these full bridge MOSFETs are driven by an E556 IC and 4013 IC. We'll discuss that in detail later on. And then here is a microcontroller for the control of the inverter. Basically what this microcontroller is doing is controls the on-off operation. It controls the temperature, the fan running. It also controls the display, which shows the condition of the inverter, and also there is actually a program to run the 50 Hz drive for the full bridge here, and there will be options for here the driver. I'll show you also the option of running this full bridge using power switch modulation to produce a pure sine wave output. Here is the DC to DC power supply from the solar module or the battery supply. It actually changes the 60 volts maximum in to 15 volts for the control supply. 15 volts, then you actually linear regulate it to 5 volts for the microcontroller. So you have 15 volts to power the power switch modulation. I see the TL494 here, and also to power the driver circuit, and also the voltage for driving the MOSFETs. This is a high frequency Ferrite core transformer. I have used the ones from an old inverter board, the Thermadyne inverter, and it's actually an EER42 × 15. If you Google this number here, you'll get those transformers. And you have your filter plus, because this is a modified square wave inverter, so just an inductor pair there, filter inductor, fuse filter inductor, voltage dependent resistor, or your MLV metal oxide varistor, and then the relay there that is controlled by the microcontroller for controlling the output power there. And then here is the 50 Hz drive using the NE556 and the 4013 D-latch. Quite a common circuit used for in inverters. And then here the display that shows you the condition of the inverter. I'll do the video for the control circuit of the microcontroller. I've used the Atmega 8. This button does the function control. Like you can choose between battery supply or solar supply, and you also use the as a reset button. It's also used as an off button, and then here the thermistor for temperature control, a regulator, 5 volts regulator. This inverter will run without a battery, will run straight from a solar module. Well, 300 volts, depends on the load and also the availability of solar energy, meaning the sun. If the sun is good enough, you can actually run this inverter to power a television up to 40 inch, charge your laptop. I'm using a 365 watt Canadian solar module on this inverter. I've built one, and it's actually powering a TV. I can power my TV, I can power my laptop, I can power lighting, and my power amplifier. Quite big power amplifier that I use at the same time with a 365 watt solar module. Right, here is now the main description of the 48 volt PV direct inverter that I have done. If you feel like you can skip this blah blah that I am doing, well, you can just download the circuits and start working on them. I start off with the input side, and then we go on step by step. Right, the whole idea of an inverter of this type is actually to produce a high voltage of around 300 volts. My inverter is running on 246 volts. So here we have your supply, which is the solar module or a battery of 48 volts, and this inverter, as I said, it runs from 30 volts to 60 volts and any supply in between. Right, so you have that voltage input, and then this voltage is applied to the transformer, and the transformer must be switched at a frequency I recommend not more than 100 kilohertz to produce the high voltage through the bridge rectifier there. Right, now to do that you have to have a pulse width modulation IC, the integrated circuit. I have chosen the TL494. Right, you can use the SG3525, or you can use any other pulse width modulation IC. The frequency that I've chosen on my inverter is around 40 kilohertz. I've used 50K. Let me zoom it so that at least you can see the components on that section here. Okay, right. I've used 50 kilo ohm resistor here with a 1 nano capacitor there. So this I see, if we check, we have 50 kilo ohm resistance there and 1 nano. Right, here's the graph, the log graph of frequency versus the timing resistor and given capacitor. The 1 nano microfarads capacitor is this line here, the topmost here. That's the 1 nanofarad. Okay, 0.001 microfarad, and the 50 kilo ohm resistor is here. 50 kilo ohm, where they cross with that one will give you the frequency. So here you have the log graph, which is 10 kilo ohm, 10, 20, 30, and at around 40 there, that's where you see they are meeting there, 40 kilohertz. So this is how I have done my inverter, 40 kilohertz switching, plus minus, of course, the differences of component tolerance. Right, switching here, the MOSFETs. I have used this configuration for the driver for the MOSFETs. Remember, the MOSFET, they have capacitors to charge and discharge here, and the MOSFET must also be able to handle the 48 volt supply here, maybe 60. So I have chosen the on my inverter. I've actually used the same MOSFETs that I used on the output. The transformers are actually coming from welding machines. You can search for EER42 X15 transformer on the net, and eBay. You can get those transformers, or you can also get them on Alibaba, AliExpress. The bridge rectifier must be able to handle at least 500 volts, so you can use separate diodes, or you can get a bridge module, but the parameters are that you should be able to handle 500 volts, and also the current that you will actually be targeting. Like if you are going for a 500 watt inverter, it means it's around 10 amp, so you normally would double the current rating, so 20 amp diode should be able to handle the power of the load. So they have two coils, but you should watch on how you actually wire the primary side, because you should actually the turns direction matter here. You must be careful on that one, right? Yeah, now we go on. Right, you produce the 300 volts here, or I'll actually refer to 300 volts here, but it depends on your design now. Right, the capacitor here must not be very big. 470 microfarads will actually suffice, but this capacitor must be able to handle for at least 400 volts. Okay, I've used the 470 microfarads, 450 volts, but the first important stage is done. Now, how to maintain a fixed voltage there? You have a feedback path here to the pulse width modulation IC via this path here. Here you adjust this resistance, and normally use the 2 watt resistor here. Adjust that value so that you have the value that you need there. These values that I've used is the values of my inverter, and it goes to the non-inverting input there on the pulse width modulation IC. The capacitors, please remember, these capacitors are necessary. They are necessary. I tried to leave them out, but the circuit on frequency was not very stable, even on feedback. There was a time when I actually increased the frequency. I used a 3K resistor here. The frequency was very unstable. I could actually hear the transformer like hissing, and then when I was using my small cell phone there and using as a light, the transformer would actually respond to the signals of the cell phone, like going the sound that you hear when you actually put your cell phone close to an active speaker. So yeah, the frequency, please, if you run it around 40 kilohertz, I think it's enough. It's okay, not beyond 100 kilohertz. Right, and then now you have the 300 volt power here. Now the 300 volt power, the choice of choosing how you would want to switch it out. Right, let me zoom back in, so that we have our circuit in view, big area. Right, no, this is how I have done my inverter, using transistors to drive these MOSFETs. Right, these transistors are just switching off the MOSFETs, and then this resistor is responsible for switching on the MOSFET. The driver, as I will discuss it, is actually a simple driver, but a very tricky driver. So I'm using 4 lines of driving this bridge. This is a full bridge setup, and then I'm using the same on my inverter, the same MOSFET that I've used at the input side, 20 amp, 500 volt. I could have used the IRFP260 here on the driver side. Right, the driver side is basically I've used the 555 timer, the double one, the NE556 and 4013, CD4013. Right, so what this circuit does is an area that we need to discuss further. So for now, I leave it. This is how I used it. This circuit will actually have 4 lines of output to drive the full bridge setup there. Right, on the output of the full bridge, which is the output of the AC output, there is a relay that actually switches the output there. But as you can see, the filtering does not have a capacitor. If you put a capacitor here, the X2 capacitor, that is, of course, you have a square wave here. It's a modified sine wave, but well, a modified sine wave is actually a modified square wave, basically, not a sine wave. So if you put a capacitor here, you tend to actually load the MOSFETs there. They normally don't like it. In any case, the load that you would connect here would actually also have a capacitor there, like TVs, laptop power supplies, and all that. Computers, they already have this setup here. So this is just done for loads that do not have this setup here. The MOV or the varistor there is just to check the voltage. If we have a higher voltage, the fuse will blow, and because this one will short and that one will blow, and then you actually to prevent damage to the equipment there. Right, so that's the output side. Remember, I will discuss about this circuit here, the driver circuit here. Right, but before then, what I want to discuss is, as you can see here, is disconnected there, and here there is an open end there. Right, you have a choice, because on the program of the microcontroller, here the microcontroller, there is a signal output that actually would be able to drive the 4013 D latch there, but I have not used this output there. I've used the NE556 output on pin number 9. Right, let me zoom it. I've used the pin number 9 output there. Right, pin number 9 is actually connected there. Right, okay, so I'm driving the 4013 using the 555 timer. Right, and I do not have the feedback from the high voltage, because you can actually have a feedback path from the high voltage power here from that capacitor through a very high ohmic resistor going through to that part here. But here I fixed the pulse width. I fixed the pulse width. Well, that's double regulation, because already I fixed my voltage output there, and then I fixed the pulse width here, or the wave shape here. It's fixed, so that I will actually be driving the full bridge with a fixed wave shape there. Now, so this is an option. You can use the output from this microcontroller, or you can wire this one. When you choose to use the microcontroller output, you do not need to have the NE556. You just need to have the 4013. And then later on, they also have a discussion on how you can actually use a pure sine wave circuit that I have designed. I have not yet used tested it on an inverter, but it's running, it's giving out a pulse width modulation signal. This would be my next project. You actually would take out all the NE556 and the 4013, and then drive the bridge with the IR2113. So yeah, that's why I've actually written here for pure sine wave, replace all this side of the blue line, which is this side here, with the pulse width, the pure sine wave inverter circuit. We'll discuss about that one. That is another option that you can have if you choose to have a pure sine wave output here, rather than the modified square wave, which is normally called the modified sine wave output. Right. Next, on the microcontroller side. The microcontroller side, there is a video that I'll do for this the microcontroller output, how it is going to control the inverter. But basically what it does is there is the temperature sensing here, which is the thermistor negative temperature coefficient. When it is getting hot, because this is mounted on the heatsink for the MOSFET. Basically the 30 negative temperature coefficient, or the temperature sensor, must be mounted here, this area here, either on the transformer or on these MOSFETs. What I have done is I have mounted on the heatsink where the MOSFETs are mounted, so that you check the temperature of the input, and then when it gets hot, the resistance decreases, and then the microcontroller senses that, and then the fan will start running when it gets to a set temperature. This is a 10 kilo ohm NTC compared to the 10 kilo ohm, and all this area here is powered by the 5 volts. Before I forget, when you are actually running the 4013 with the microcontroller, please use 5 volts power supply for the 4013. But when you are using the NE556, you can actually use 12 volt to power the 4013. That's because your high level from the microcontroller is actually a 5 volt, and you would want to have a high also being understood by the 4013 is 5 volts. Okay, that's another area that you should actually be aware of or take care of. Right, and then a buzzer which actually warns the voltage level. When the voltage level from the supply gets lower or higher, it will give you a buzz. And then the LEDs are for display, state condition display. I'll do the video on the control of the microcontroller here, though I am not going to do the video on the Atmega microcontroller, because my simulation on Atmega is very slow. This is running on my inverter. I'm using Atmega 8. These buttons, they are momentary push on buttons, meaning you push to make it on, and they actually ground the inputs. When you push it on, it will ground the input. Right, so when you push this one on and you release, then the LEDs will indicate, and then after some seconds this relay come on, and then a few seconds later, I think 3 seconds, I set it, the output relay comes on. And then when you want to turn it off, you press this button and then it shuts down. This, when there is an error like a low voltage error, LEDs will indicate that you actually have to reset using this button here, the off reset button. When you want to choose whether you are using solar only or solar priority input power, you press this button for long, and then you can change around whether you want battery or solar priority. The default is solar priority. When you switch on, when you power the circuit, it goes to solar priority. So when you have to press this button for 3 seconds or more, so that it changes to battery priority, meaning the levels of the input voltage is now what the microcontroller will be testing are now different between the two. And the LED here, the mid LED, the D7, will actually show you that. I will do the video on that, which will be part of this discussion or this video series.